Good morning, everyone, and thank you so much for joining us for today's Nexus Leadership and Innovation webinar series. We are so excited to have you join us for this engaging series. My name is Liz Mahalski, and I'm a program manager for Nexus at Michigan Engineering. Just a little bit of housekeeping before we begin. There will be a dedicated question and answer period following this presentation. I would like to announce today's speaker, JD Marhefko. JD is the ZF VP of Quality for its Electronics and ADAS Division U. This role came on the heels of the Borg Warner purchase of Delphi Technologies, where JD was the Global VP of Quality and Warranty. JD was also a VP of Operations Americas for SAF Holland and the SVP of Quality Lean and EHS for Accuride. 4 Accuride sites won the AME Excellence Award, and one site won the Industry Week Best Manufacturing Plant of the Year. In 2020, JD was inducted into the inaugural USA Women in Manufacturing Hall of Fame. JD is an ASQ Fellow, a Sheehan Medalist, CMQ/OE, CQE, CSSBB, and a Master Black Belt. She is also an ASQ Certified Trainer, Step Ahead awardee, and in 2018 was recognized by Cranes as a notable woman in manufacturing. She holds a BSc and MSA. JD is a past chair of the ASQ QMD. She currently supports the ASQ QMD in a variety of capacities. JD has co-authored several books and articles on lean quality systems, but most notably Accuride's Corporations, Lean Management's 50-50-20, as well as a small vignette depicting their family's journey with autism, a sample size of 1. I'll now turn it over to JD. Welcome.
Thank you, Liz. It's a lot of acronyms in there. Just means that I've been in manufacturing for a very long time. Today, we're going to be talking about measurement system analysis, MSA, and process capability, CPK. This is a technical, interactive session. So hopefully, if you can, please have a calculator handy and maybe a pen and paper.
And JD, your screen is not shared currently.
Oh, all right. Well, let me reshare it because I was sharing before. Just one moment. Let me find where I'm at. All right. Can you now see my screen again?
We sure can.
Yay. Okay. So we'll start again. So what we're going to be doing is we're going to be doing a rapid high-level overview of how process capability generally works. And that's that diagram on the bottom left-hand side. And it would be helpful for you, like I said, if you had a paper and pencil, calculator handy, because we're going to be a little interactive here. And then from that, we will do a quick overview of how variables measurement works, measurement system analysis, from the gauge repeatability and reproducibility perspective. We're not going to get too much into the details of the formulas. We won't discuss how to calculate a percent gauge R&R. That's a lot of fun, but not for this session. And then we're going to connect those two together to see why they're so interdependent on each other. Let's talk about process capability, CPPP. This is a quick index that the customer uses to compare how fat the process is compared to how fat the specification is. And the first thing we need is the width of the specification. And in this example, we're using a spec of plus or minus 10. And that total distance is the upper spec limit minus the lower spec limit, 10 minus a negative 10, which gives us a width of 20. You can do that on your calculators, and we all have 10 fingers and toes, so we have enough digits to make that happen. Now, if we want to have a process, here in this process, I have these parts that I have taken measurements of. All of those X's are different measurements. I've got one part that measured a 2. I've got 3 parts that measured a 3, and so on. And in total, I've got 20 pieces that I've measured. The average of those 20 pieces is 5. I take all those readings, I add them up, I divide by 20, and I get an average of 5. Now you see, I also have a standard deviation of 1.67. I'll show you later on how to get that number. But for right now, what we want to do is to see how fat our process is. And by doing that, we calculate what we call the upper tail of the process. We take that standard deviation and we multiply it by 3. So we're going to take that 3 times sigma. That's what that symbol is. 3 times 1.67, and that's approximately 5. and we're going to add that to the average. And that black line that you see, that takes us from the average to the process tail, the upper tail. 5 plus 5 is 10. And what this is saying is that in my process today, as I'm running my activities, the biggest part I found was an 8. That's what I found. I got an 8. But if I continue to take parts, if I continue to take samples, I should find a 10 eventually. There's a 10 in there somewhere. I just haven't found it yet. So this is giving me a prediction. It's giving me a probability. It's telling me that eventually my process is going to be as big as 10, even though I only found an 8. We do the same thing on the other side. We say, okay, we're going to take our average and we're going to subtract 3 sigmas, 3 times that 1.67, and that's going to say 5 minus 5, and that puts our lower tail at a 0. And again, I haven't found any zeros. The smallest part I have is a 2. That's okay. But this is saying that the whole width of my process from tail to tail is going to be from 0 to 10. And there are 6 sigmas in there, 3 on the right-hand side, 3 on the left-hand side. So the base of my bell, the base of my normal distribution that I'm dealing with here is 10. Now, what this means, though, is that because this is an estimation, it's a probability. This only covers 99.7% of our stuff, and I call this the Bell umbrella. The Bell umbrella covers 99.7% of our process results, as long as it looks like a bell. That means I'm going to have about 3 per 1,000 units outside of my bell. In this case, it's okay on the left-hand side. I'm going to have about 1.5 parts per 1,000, lower than 0. Well, that's okay because my spec is a minus 10. It'll be out of the bell, but inside the spec. On the right-hand side, however, I'm still going to have a 1.5 out on the right-hand side. It's going to be outside of the bell. That's normal. It's natural. But it will also be outside of the spec. So my bell is shifted too high for me to have all good parts going on. For me to do my process capability average, I'm going to still look at that whole process width of 20, of minus 10 to positive 10, and I'm going to divide it by how fat my whole bell is from 0 to 10. And it fits in there once, twice. So with that, my process capability, my CP, and the CP talks about the whole bell, all 6 sigmas, 3 sigmas to the right side of the average, 3 sigmas to the left side of the average, total of 6. My bell fits in there twice. That's a good ratio to have, but we remember that we're still going to have those little parts outside. Excuse me while I deal with my cold. Now, when we take an extra step, and we take an extra step called the process capability, and it asks us if our bell is centered. And that is the same activities, but only using half of the bell, only using 3 of the sigmas. So there would be a CPK for my upper side and a CPK for my lower side. For my upper side, I want to see what that distance is between the average and the spec line, and that's between the 10 and the 5, so that's 5 wide. And then I know that my process half is that 3 sigmas, a 3 times 1.67. And that half of the bell fits into that half of the specification from the average to the spec line. It fits in there one time. And that's not considered a good result for most of us, because I know that I'm going to have that little 1.5 hanging out there on that right-hand side. If we look at how this formula works for the lower side, we have we're going to do the same kind of thing. We've got that distance from the average to the minus 10, so that's a distance of 15, and we've got the left-hand side of the bell of 3 sigmas, 3 times 1.67, and that's going to fit in there once, twice, 3 times. So it's 15 divided by 5, and that 5 is that 3 times that 1.67, that 3 times that sigma. That's telling me I've got a lot of room for that half a bell to fit in there. The bigger the process capability, the better off you are. We still have to remember, though, that because we're doing an estimate, when we're doing process capabilities, we usually haven't taken 100% of all of our readings. We've taken a sample. So we don't necessarily have information on 100% of the population. And because of that, the bell will only cover 99.7% of your results. So that's an important thing to remember. That bellbrella, that bell only covers 99.7% of your stuff. And that's what it's supposed to do. So we're always going to have 3 per thousand that are kind of hanging on the outside. So let's look at what this means to you. If I have these big black process specifications, if this is my lower spec and my upper spec, and if this is what my bell is doing, each sigma that we have, and we draw our bell with 3 sigmas, we know how much of our product results are within each of those sigma bands. So within plus or minus 1 sigma, we have 34.2 plus 34.2. So we've got 68.4% within those blue lines, or plus or minus 1 sigma. If we add in that second sigma, that's going to grab another 13.6 on both sides. So now I'm getting 95.6% between plus or minus 2 sigmas. If I get into the third sigma range, that's going to give me that 99.7% that I was talking about. And you can see the red 0.15 that's on either side. So if my bell, my distribution, went from tail to tail, and those tails lined up very close to the specification lines, I would be producing 3 parts per thousand out of spec in this particular process example. Now, let's say I made improvements to my process, and I want to shrink how fat my bell is. I'm putting it on a diet, and right now this bell is too fat for me. So there's 6 causes of variation in a normal distribution. You've got your manpower, your machinery, your methods, measurement, environment, and man, machine, method, material, and environment. So you've got these 6 things that are going on that cause your readings to have different, cause you to have different readings. And we've got to change 1 or more of those 6 things to make your bell get skinnier. So let's say we've done that. And notice that your black lines are going to stay in the same place. So my black lines are in the same place, but now we've made an improvement to the process, and now the bell is skinnier. Yay, team. So with that said, the ratio of the sigmas stays the same. I'm going to say that again. The sigma ratios stay the same. My bell has gotten skinnier. My plus or minus 1 sigma, that's 68.4%, those parts are now in a smaller range than they were before. Before, they took up more room. Now they take up less room because my variation has been reduced in the process. My plus or minus 2 sigmas is reduced as well, but that covers 95.6% of my results. The same with the third sigma. But now notice where that 0.15 has gone. It has moved from outside of the specifications to inside of the specifications, because now my bell is skinnier, and they've been brought in. They're still outside of the bell. They always will be, and they typically hang out around that 4th sigma process. Now, the 4th sigma, we never ever really get to 100%, but we get to 99.994, and that's a lot better than 99.7. If I'm making a safety product and I'm making 1 million units a day, 99.7 isn't good enough, because I've got parts that are being produced out of spec that are going into the population. Even at 4 sigma, while it's definitely better, it's still not considered as strong as you'd want it to be. But those out of spec units, they're outside of the bell, but inside of the spec line. So now let's say we make another improvement to our process and we make it skinnier again. So the black lines are still in the same place. The sigmas are now skinnier. the ratios are still the same. Within plus or minus 1 sigma, I still have 68% of my parts. Within my second sigmas, plus or minus 2, I've got 95.6. I still have those red parts that are outside of the bell. They're still within that fourth sigma range, and they're close to the tails. They're close to where those process tails hit the end of the line there. But they're farther away. They're closer inside. They're farther away from the spec lines themselves. That's giving our process more reliability, more stability, so that if parts are produced outside of that normal distribution, they're going to be very, very close to those tail ends, and they're not going to be close to where the specifications are at. We're going to do this one more time. So now let's say we've got it super skiddy. We've got the bell even more improved. We've done more changes to it. And you can see now I can fit this whole bell inside of my spec lines twice, because my bell is taking up 6 sigmas, 3 on each side, out of a 12 sigma range. So 6 out of 12 is 2. That whole bell fits in there 2 times. And the ratio of how many parts are underneath that bell still stay the same. So those parts are still, those 3 parts per thousand will always still be outside of that bell. They're going to be very, very close to that 4th sigma point. And you can see that they're very tight within, and they're farther yet away. When you hear people call about 6 sigma quality, when you say, oh, it's 6 sigma, what it means is that we have room. We have room for 6 sigmas between the specification. Let me turn on my pointer here. You have room for 6 sigmas between the average and the spec line. And in this case, my process is stopping at the 3rd sigma, which is good. But I've got room for this to fit in there twice. The whole bell fits in here twice. And that's really helpful for us. This is where we really want to be when we start a new process, where your whole bell can fit inside this twice, especially if you're dealing with a product or a process that is safety-based or critical for form, fit, and function of the product. When we talk about process capability, we look at it at 2 levels. We look at it at an initial and long-term. Initial capabilities, when you run that process for the very first time, I've got my best operator. I've got perhaps 1 or 2 lots of raw material. I've got the same, it's in 1 shift or 2 shifts. I've got 1 machine set up. I've got no maintenance happening. I've got, the same ambient conditions. It's the same humidity, the same temperature. So a lot of my variables are held very constant. And that's the best my process is going to run. And we call that an initial process capability. And in this case, in this example, I've got my spec lines here, and my bell can fit in here 2 times, which means that my process capability is 2. If I had these 3 little parts hanging out, they'd be outside of the bell, but inside of the spec lines. And that's good. When we want to talk about long-term process capability, this is where my bell's going to be moving around a little bit. I've got different setups. I've got different shift changes, different operators, different raw material lots coming in. I've got maintenance happening, and they're adjusting the machine. I've got winter, spring, summer, fall. I've got all the other different variables that are happening. The man-machine material, method, measurement, environment, those 6 common causes of variation. And my bell's going to move around. It's going to get fatter. It almost always does, unless something very specifically has changed. So your bell, the width of your bell is going to get fatter, and it's going to de-evolve a little bit. So some people say that it typically moves back and forth by about 1.5 sigmas. Depends on whose book you read. In my experience, doing this for over 35 years, these bells move a lot after you set them up. The processes just move. The problem is that you want to be able to control it so it doesn't move too much. So whatever your estimate is, we want to make sure that your long-term capability stays within 1.33 so that you've got room for that extra sigma out there, so that that part, those 3 out of 1,000 parts don't fall outside of your specifications. So now what we're going to do is, this is where you're going to be needing your pencil and paper and calculators. This is a table to help you calculate how much scrap you're producing. This is a part per million table for one side of your bell. So it's only going to talk about half of your distribution, one side. And if you want to look at the other side, you do the same thing, you just do it twice. So I'm going to go through a couple of examples here to show you how this works. If I have a process, this blue bell here is very fat. It's creating out of spec product. I can fit in 2 sigmas out of 3. The process capability is 0.67. So I've got 0.6. So the A point B is 0.6. So I go down to 0.6. The C is the 0.7. So I'm going all the way across now till I hit that 0.07. And that's telling me that I'm going to have 22,216 parts per million out of spec just on one side. So the area under that curve after the spec line is going to have 22,216 parts per every million that I produce. That'll be out of spec on one side. And because my process is centered, I'm going to have the same risk on the lower side. So in this case, I can multiply that by 2 and know that I'm going to have 44,432 parts per million out of spec. If I wanted to convert this into a percentage, I would divide that by 10,000. Excuse me. So that's how this chart works. It's for one side. If your process is centered, you can calculate that easily for the second side. You just need to know what your CPK is. Once you know what your CPK is, you can look in this table and it will tell you what your ppm will be. And I've got this little half a bell on here to help remind people that it's only for the one side that you're looking at. Here's a different example. If I have a process capability of 1.0, and we looked at that, we have 3 sigmas that fit between the average and the spec line. I'm going to go 1.00, so down to 1.0, 0.00. That's 1.35. So that's 1,350 part per million for one side of the process. And to get my non-conforming, I would divide that by 10,000. And then I would, since again, this is multiplied on both sides, and you don't see it here very easily because people often don't see or they forget that this bell is only covering 99.7% of our process. And that means I've got 3 per 1,000 that are going to be outside of those tails. So it's real easy to forget those parts if you don't know what's going on behind the scenes. So if the bell were centered, we'd have a 2.7%. Most people round that off to 0.3%, which is where we're getting that 99.7%. This is the 0.3, 0.3%. That's out of spec in this kind of example. Going to the next one. Here we have an example where the distribution is now shifted to the right, very much like the first one that we started out with. This bell fits in the whole process twice, which is good. The process capability is 2, but because it's so shifted far to the right, the CPK is again 1.0 on the right-hand side and 3.0 on the left-hand side. So again, going back to that 1.0, it's still 1.350, and now it's going to be capturing that part and a half that's out on the right-hand side only, because the part and a half that's out of the bell on the left-hand side, it's out of the bell, but in the spec. In this example, we have the bell is centered. It has moved back to the center. This is a 6 sigma bell because the bell fits in here twice, and I've got room for 6 sigmas between the average and the spec lines. So the bells are always drawn with 3 sigmas on either side. And in this case, the CPK is 2.0. So I'm going down to 2.00. And essentially, we call that a very, very small number. I'm not going to say all those zeros because I'll get lost. But this is considered Six Sigma quality. So now let's talk about how to calculate sigma, because it helps us to see where that number is coming from and why the bell gets as fat as it does. Because sigma tells you how fat that bell is. So I'm using three values here. I've taken three readings, a 2 and a 1 and a 3. So I've got three numbers. My sample size is 3. I've got three values. The average is 2. 3 plus 1 plus 2 is 6. 6 divided by 3 is 2. So the average is 2. And you got this wonderful, lovely little Greek formula over here. So I'm gonna plug and chug so that you can see how this works. So I'm going to take the average each time, which is the blue 2, the average for each time, for each number that I have. In this case, I've got three values. 2 minus the 2, which is the first black 2. 2 minus the 1, which is the second value, and then 2 minus the 3, which is the third value. Each of those, it would be squared. And then I would divide that by my sample size, which is 3 minus 1. And we're going to go through and do the math. So 2 minus 2 is 0 squared. 2 minus 1 is 1 squared. 2 minus a negative 3 is minus 1 squared. And I'm going to divide that all by 2. 0 squared is 0. 1 squared is 1. And a negative 1 squared is 1. And I'm still going to divide all that by 2. So now I've got 0 plus 1 plus 1, which is 2. I'm going to divide that by 2. 2 divided by 2 is 1. And that's the square root of 1. And that all comes to 1. That is a very hard way to get to 1. But it works. So let's see what it looks like. If I draw my histogram, I have a value at 1, a value at 2, and a value at 3. You see my three x's. But my sigma's 1. So I'm going to take 3 times 1. And so 3 sigmas to the right. I'm going to add that to my average, which puts me at 5 on the right-hand side and at minus 1 on the left-hand side. So with this little example, it says if I keep taking readings, even though my biggest value was a 3, I'll find a 5. And even though my smallest value was a 1, I'm going to find a negative 1. Now, this is just what I call a math exercise. In real life, we would not calculate sigma just on 3 values. That's not technically correct. You need 30 or 40 samples or more to see if your process looks like a bell, if it's normally distributed. In this case, with 3 values, you can't tell that. I just did that so that you could see the exercise and how to run this. If you end up having 40 values, 50 values, 1,000 values, this gets very, very long underneath there. And that's why it's very helpful to have a software such as Minitab or JMP or SQC Pack, any of the softwares out there that help you do this. So now we're going to give you a little bit of homework or a little bit of exercise. Whatever your last name is, pick one of these rows, and I would like you to go ahead and calculate the process capability upper, and the process capability lower. And the 4 distributions are below. So here's the first one. In every case, the upper spec limit is 10 and the lower spec limit is 0. So always 10 minus 0 should be 10. And then you're going to take for your process capability 6 times your sigma. The sigma is different in some of these. And then you're going to see how many times does the blue bell fit inside of the spec lines. The whole blue bell, all 6 sigmas worth. For the CPK upper, you're going to take the upper spec limit, which is always 10 in each of these cases, and you're going to subtract it from the average. You can see that the average may be different depending on which example you're taking. And then you're going to divide that by half of the bell, 3 times your sigma. How many times does this half bell fit inside of that distance? And then you're going to calculate the CPK lower. This is going to be taking the average which may be different in each example. And then you're going to subtract that from the lower spec limit of 0. And then you're going to divide that by the lower half of the bell, 3 sigmas. So hopefully you should be working through those, and I will give you another minute or two to do those, and then we'll go through the answers on how those worked out. And Liz, if you could see in the chat, if anybody can put into the chat how much, if they're doing okay or if they need more time, that would be good feedback to have.
Absolutely. We don't have any responses yet, but I will keep you posted.
So in total, you've had about 3 minutes, about 1 minute per formula. Hopefully that works for you. And we're going to go through the answers. So in the first one, the blue bell here, the process capability is 0.67. 2/3 of the bell fit within the spec lines because we have 1 sigma hanging out on each side. So out of 6 sigmas, 4 out of the 6 fit inside of the spec line. And then the same for the upper and the lower process capability. And you can see the math worked out here. And this is roughly 4.4% that's under the bell here that'll be outside of the spec in this kind of process. In the next one, we have, and this is a very deceiving one because it looks like it's okay when it's really not, because you have that 1.5, 3 parts per thousand that are going to be hanging out there creating problems for you. So in this case, the process capability is 1. The bell fits in there 1 time. The same for the upper and the lower. And the reason why these two are the same all the way across is because the bell is in the center position. Only when the bell is not centered will the capabilities be different. In the third one, we can see the process capability again is 2. This bell fits in there twice. And from that, the upper process capability is 1. The CPK upper is 1. Those 3 sigmas fit between the average and the spec line 1 time. And on the lower side, between the average and the lower spec line, these 3 sigmas fit in there 3 times. And in the last one, we can see that this fits in there 2 times. And we would technically state that this is 0 parts per million in terms of nonconformance. So when we look at a normal distribution, when we look at a bell, Taguchi loss function says the farther away you are from the target, typically it's the middle. It's not always the middle, but typically whatever that target is, the farther away you are from it, the more loss you're going to incur until you hit the spec lines, and then you're going to have full loss of the product. So now we're going to switch gears from capability into measurement system analysis, MSA. There's generally 2 kinds of MSAs that you do. We do them on variables, things that we can measure, and things that we make a determination on, like pass, fail, it's good, it's not good, it's scratched, it's not scratched. Those are called attributes. So when we measure or make an assessment of an item, we want to make sure that our result is correct. If it's not correct, we have 2 risks. We call it the alpha or the beta risk. Alpha means I'm rejecting a good part. And I like to say, oh, darn, I've thrown away a good thing. So that costs us more money, but it doesn't hurt the customer necessarily unless we charge them more for parts that we throw away. The beta is bad. Beta is when we accept bad parts and we don't know it. I'm going to restate that. Beta is bad. It's when we accept bad parts and we don't know it. Our people are making an honest decision, but they have information that's telling them that the part is good, but it's really bad. And we'll show you how that's happening. So as people, as humans, we usually believe what we see. When we talk about the measurement system, the things that we can what we can measure, length, width, height, speed, things like this. We use instruments for those. There's generally we use what's called a crossed gauge R&R. A nested one would be for destructive testing. And then we're not going to go too much into attribute agreement analysis for this example, because this is talking about variables gauge R&R. Attribute is, again, a go, no-go. And this is where we're using our senses to make a decision. So when we're using measurement system analysis for variables, we want to look at accuracy. And in this first bullseye, this is a very accurate and precise set of measurements. They're all right in the middle. In the second one, it's accurate. They're all clustered together, or excuse me, it's not correct, it's inaccurate, but they're precise. They're clustered together, but they're in the wrong position. Accurate but imprecise, so the average comes out right, but each individual reading is a little bit off. And then you have the scattergun approach. So accuracy is assessed by calibration. And one thing we have to keep in mind is in calibration, it's very important for us, but most of us rely very heavily on calibration and don't take some extra steps to make sure that the measurement system is working well. This does include bias and what we call linearity. Precision, how far off that instrument precision is the distance between the right reading. That precision is done through a variables gauge R&R evaluation. And that's where you do a series of measurements, a series of tests with a gauge, with operators, with people, and see if you can get the same readings over and over again. And what it comes out with is an error reading. And we don't want more than 10% error in general on gauge systems. And this error is broken out into two pieces. How much of the error is due to the gauge and how much of the error is due to the human piece. If this is an automated gauge, then the human piece goes away. But still, you want as less amount of error as possible. If you have a gauge with 100% error, you can't tell if you're getting good readings at all. So if I do have a gauge with 10% error, I can still make a mistake in how I'm reading my parts because my gauge won't be perfectly accurate or it won't be perfectly precise. And this is what we want to be able to measure. We want to see how imprecise it is so that we can make good decisions. Our people can make good decisions. We also need to make sure how well we can read the gauge. Here you see a clock, and the clock it's 10:10 at 35 seconds. Excuse me. If I remove my discrimination, how good I can read this clock, I can read this clock to the seconds because it's got a second hand on it. If I take the second hand off, I can still tell that it's 10:10 because now I have the minute hand. If I take the minute hand off, all I know is that it's somewhere around 10 o'clock, but it's not exactly 10 o'clock. So that ability to discriminate is based on how well we can read that instrument. And the gauge resolution needs to be at least 10% of the tolerance, and that is an international standard. You need all three of these pieces. It's like a three-legged stool. You need all three of these pieces to be able to make sure that the readings that you're getting are correct and that you're making the right decision on your products. So now we're going to put both of these together. We spent a lot of time up front on process capability, trying to get you to understand, how it works for you. And in this example, I have a process capability of 1.0. My bell fits inside my spec lines one time. And that means I'm going to have parts that are reading at both ends of the spec, at +10 and at -10. Now, if I have a gauge that has 10% error, and if my gauge reads this black X, my gauge reads 10, my operator or my automated gauge function will accept that part. However, because the gauge itself has 10% error, it's going to make the wrong decision at least 1 out of 3 times every time it finds a 10. And it's going to accept a bad part 1/3 of the time when it finds a 10. And that's a problem. So if I have a process that's too fat, like this one is, and my process is producing product at the spec lines, at the where the specification is at, and I have a good gauge with 10% error, I will be forcing defective product into the field because the gauge will make the wrong decision, or the human using the gauge will make the wrong decision because the gauge is telling them it's a 10, but due to the gauge system error, it could be a 9 or it could be an 11. If my gauge read a 10, my operator or my process will reject it like it should. But 1/3 of the time, it will be throwing away a good part. And that's an alpha error in this case. So it's important to understand what your gauge error is and how your process capability is working for you. In this example, we have now put the process under improvement. This is a 1.67 process capability. I can fit 5 sigmas in here from tail to tail. And now if my part reads a 6, I still have a 10% gauge. It could be a 5 or it could be a 7. That's okay. I cannot make an alpha or a beta error here. I am always making the right decision with the parts. So in this case, when we're starting a process and we want to make sure that we're making good decisions with our gauging system, a 10% gauge error is acceptable and allowable in industry. That's pretty much the best you're going to get in most cases. You can definitely get better and lower gauge error results, but 10% is what is accepted across the world. And if we have a process that's too fat, you will be creating alpha and beta errors. You'll be releasing parts that are out of spec into the field, or you will be rejecting good product that you should be able to pass. Making sure that your process is skinny enough when you start out and holding it to this level of variation, holding it down so that it doesn't get too fat, so that you have room for those part and a halves to come out of that bell on either side. With the 10% error rate, you should be okay, and you would not have alpha and beta errors with your gauging systems. So I know that was really fast. I hope you were able to follow along. We need to be able to do gauge R&R everywhere through the process. We do measurement system analysis in engineering and testing. We do it in quality labs. We do it at supply chains across our suppliers. Maintenance, they use measurement systems to evaluate that the equipment is working right. We use it in the production lines. Measurement systems are done everywhere. And we need to be able to make sure that gauge R&R is done in all of those places to ensure that you have good results. So we had a rapid, high-level overview of how to do process capability, short-term and long-term, for the full capability and for the half capability, and we practiced them, and we connected the process capability to the gauge R&R tolerance, so that we could make sure that we were not protecting ourselves from alpha and beta errors. And this is a superpower. A lot of people don't really connect these two things together, and this can help you make a difference in your business. So with that, I'll thank you, and I'll open it up for questions, and I'm going to take this off of the show so that I can see anything on the, so I can see what's going on. So Liz, are there questions? Do we have, I see things in the chat. What can I do to answer questions for anybody?
Please feel free to unmute or pop your questions in the chat.
If anybody does have any questions or they want to, learn more about this, feel free to join me on LinkedIn. And I'll be happy to answer anything that people have.
Hi, JD. Sorry, I have one question. So we mentioned about the PPM and the different PPNs depending on the different CPK value.
Yep. Yes.
Or does
And
it
you're,
much
and you're, I'm sorry, go ahead. Sorry, Zach, I didn't hear your question. Can you see if the question is going into the Zach, Zach's question is going into the chat, Liz?
It is not yet, but Zach, if you would pop it in the chat or feel free to unmute. In the meantime, we also have another question. What is the acceptable CPK value?
It depends on the type of product and processes you have. If you are making a safety product or if it's a critical feature, you would 1.33 is your minimum process capability that you would want to be having. Something so that your process capability allows those parts that are outside of your bell to fall inside of the spec line. If usually some customers require a 1.67 so that you have room for 5 sigmas, but between 1.33 and 1.67 is where most people go. If you are in a non-safe, if it doesn't matter, if safety is not such a huge issue, making tabletops or flooring or something like that, 1.0 is sufficient. This works for both low volume and high volume. I did see that come across. Let me see if I can pull up the chat. Yeah, Bill Levinson, thank you for your comment there. Inadequate gauge precision. Yeah, if gauging isn't right, you make a lot of mistakes and it gets out into the field pretty quickly. We do not, guard banding is helpful. We didn't get into the issue of guard banding here, but if your process is too fat, if you have a process that isn't working well for you, you can, set your measurements to be before your specification limits. You end up rejecting more, but then you protect the customer. For a lower volume manufacturing company, size of 30 is daunting. That's true. Short run or low volume. So then you don't want to look at product. You want to look at your process data, process results. You'll, as long as your standard deviation is similar, you can run the same data evaluation across multiple part numbers for a similar feature. That's done all the time. So you don't necessarily have to have 30 of the same, but you can have 30 of something similar. Did Zach ever come back with his question?
Hi, JD. Apologies, my internet dropped out there. I think you answered it there when I rejoined regarding the industry standard for CPK and PPM values for safety and non-safety critical processes. So you mentioned, right, that it's 1 for non-safety critical and 2 if it's safety critical, right? Generally.
So the customers normally tell you what they want them to be. It's usually part of a customer specified requirement, a CSR. If you are making a safety critical feature, 1.33 is minimum for long term. 1.67 or 2.0 is typically required for initial, that first time out. So initial, they want it to be very, very tight first time out for safety critical. And then long term, you're allowed to de-evolve to 1.33.
That's great. No,
But
thank you for
your customers can, and some of the different automotive customers, aerospace customers, food-based customers, pharma, they will sometimes require different levels.
That's great. Thank you.
You're welcome. Any other questions that I can answer for people? So like I said, feel free to join me on LinkedIn. Be happy to answer anything else. And we do this, I do give these kinds of advanced operations, manufacturing-based discussions on a regular basis across the world through American Society for Quality, ASQ, as well as through the University of Michigan Nexus program. And we have several series set up to go deep dives into some of these very applicational, excuse me, hands-on things that you don't necessarily get this in college. And you don't always get it in your production environment from your supervisors. So this we try to make this very relational to what you have going on in your world. There was a question that just came in regarding ADAS. So those are the advanced driver assistance systems. Those are like your cameras, radar, LiDAR. When you're driving your car, how it helps your car to stop so that you don't rear end somebody in front of you. How it controls your speed control. Doing the side cameras, deploying airbags, using cameras to help deploy airbags if something is imminent. The rear backup cameras. All of those different sensors. There's speed control sensors, ECUs, electronic control units that deploy the various airbags around the vehicle. All kinds of stuff that's in there in the ADAS field. I'm going to go back to the chat. See what else was there. The slides, Michelle, or sorry, Liz, what's the plan on the slides?
You are going to be receiving a thank you email with a recording of this session. If JD, you would like to share them, I can absolutely add them. But also to answer your question about other webinar series, you will also have a link to all of our additional courses and webinars in that thank you email as well. So you will be able to see everything that Nexus offers.
Yeah, Liz, I'll get you the PowerPoint. I'll get you the deck as a PDF. The deck is shared
Perfect.
as a PDF, but you won't see all of the animations as a result.
Perfect. Does anyone else have any other questions for JD before we wrap up for the day?
Hey, thank you, everybody. Appreciate your participation. It's a really fun and in-depth topic for the morning.
Thank you.
Thank you, JD. Nice seeing you. Saludos.
Nice seeing you. Hi, Anais. Nice to see you.
Nice to see you.
Thank you so much, everyone.